in this set of lecture notes, we're going to talk about work and energy. First, let's define this terms. We'll start with energy. The most common definition that you might hear about energy is the ability of an object or a system to do work. Okay, so far so good, but this definition depends on some other definition. So let's define work. Work is the transfer of energy. Okay, so now we're kind of stuck, right? Sounds like we're going in circles. We're defining both quantities in terms of each other. So the funny thing is that these are actually the most common definitions that you will hear in terms of just simply defining these terms conceptually. Okay, but obviously we need to do a little bit more than that, a little bit better than that, if we're not going to define two terms in terms of each other. That's kind of goofy, right? So let's be a little bit more careful. I'll start by writing work is equal to change in energy. Okay, so I'm using capital E for energy here. Obviously, you're familiar with the symbol delta. So when we're saying that work is the change in energy, we're saying that that change is the transfer from one system to another, or from one object to another, or from the system to the outside of the system, and so on. So delta here doesn't just imply change, but it also depicts the movement of energy from one place to another. And to break the circular definition, we can also define work as force times distance. Sorta. If you've taken physics in high school, or even if you took some kind of integrated science in high school, I'm sure you've seen that. Work is equal to force times distance. It's a good working definition, but it's not as good as it could have been. So somehow we need to reconcile all of that and understand what it actually means. Let's start by drawing a little picture here. Okay, so let's say that there is this object here that has a force acting on it. So for the time being, I'm not going to worry about free body diagrams or net forces or anything else of the sort. I'm just going to say there is this one force that's acting on this object. And let's say that under the influence of this force, or while this force is acting on this object, let's say that the object undergoes displacement delta x. Obviously, we can define this angle theta, which is the angle between the force vector and the displacement vector. And that's what allows us to actually really develop our understanding of what work is. So instead of writing it as force times distance, I'm going to write it as force times displacement times cosine of this angle. And this is now worthy of me boxing this definition. Okay, so that's what we're going to be using for calculations. Yes, you might see it written as f d cosine theta. That's also fine. You have to be a little bit careful there in terms of what you define as distance, what you define as displacement, right? So we talked about that a little bit when we were talking in the very beginning of the semester about the differences between distance and displacement. So just be careful with that. So for all practical purposes, work is force times displacement times cosine theta. That's probably the best way of addressing work algebraically. So in other words, work is the result of applying forces. And not just applying forces to an object, but applying forces over distance. So all of a sudden, if I define force like this, all of a sudden even that other equation or that other definition of energy, that also makes sense. So basically, an object can have some amount of energy, or a system can have some amount of energy, and we're going to interpret that as the ability to do work, as in the ability of the system to either move under the influence of force, or on the other hand, to exert a force on something else, and that something else in turn will move under the influence of that force. So now it actually does make sense more than it did before. Both work and energy are scalars. So no direction, obviously. We never discuss direction when we talk about scalars, just by definition of a scalar. Okay, so all of these calculations that we do for work and energy have to be scalar calculations. Now for units. Well, unit of force is a Newton. Unit of distance or displacement is a meter. So we get Newton times meter. We define that as a joule, which I already mentioned before briefly, but I might as well write that down again. So joule, as a unit, is obviously named after a person. Now, the person joule was actually quite important in terms of physics to our next few lectures, our next few units. So Joule was the first person who actually brought thermodynamics and mechanics together. Everything that we've done so far, and even this next lecture or two, this is all mechanics, right? So we're investigating the motion of an object as a whole. We're investigating mechanical interactions between an object and other objects or other systems. We're talking about forces. We're talking about combining forces and motion, all of that stuff. So that's all a study of mechanics. After we discuss work and energy, we're going to transition to study of thermodynamics. So thermodynamics has to do with heat, thermal energy, temperature, and so on, so on. We'll get to that. So Joule was the first person to realize that whenever energy is transferred between different systems, that energy transfer can happen in terms of mechanical energy transfer, as in work, or thermal energy transfer, as in heat. Up until Joule, people thought that mechanics really has absolutely nothing to do with thermodynamics. And those two types of processes, or those two scenarios, were looked at as completely separate, different, independent of each other. So Joule was the first one to bring them together. So yes, obviously we commemorate him by naming a unit after him, but also in terms of how we're studying things in this class, we're thinking about transitioning from mechanics to thermodynamics, and this right here is our transition. Okay? Now there is one other thing that I have to tell you about this unit, so I'll write it over here off to the side. So recall that unit of torque is also Newton times meter. Okay, so be very careful here. When we talk about work and energy, that Newton times meter is defined as a joule. When we're talking about torque, Newton times meter is not the same thing as a joule. And that has to do with, well, just definition of units, but also definitions in terms of what exactly we mean by those quantities. So remember that torque is defined as a vector quantity, and work is now defined as a scalar quantity. So they're completely separate. Yes, they both have something to do with force, but the meaning is completely different. So just because you get Newton times meter in both cases doesn't mean that the origin of those two quantities is the same. So please don't confuse the two. Again, if you're talking about work, that Newton times meter turns into joule. If you're talking about torque, you just leave it as Newton times meter. And obviously in this class, we're just dealing with SI units. Okay? So units of work are joules, units of energy are joules, units of energy transfer are joules, change in energy, and so on. We will see a couple other types of units when we get to thermodynamics, but not quite yet. So for now, we're just going to deal with joules. let me also briefly mention, since we're talking about work here, if theta is equal to 0 degrees, so in other words, these two vectors, force vector and displacement vector, are pointing in the same direction, we get maximum amount of work, right? Because cosine of 0 degrees is equal to 1. Okay. We can also have the opposite scenario, where theta is equal to 180 degrees. So force and displacement vector are pointing in the opposite direction. Sometimes we can also refer to that as anti-parallel orientation of vectors. So we get minimum amount of work, right? Because cosine theta, cosine of 180 degrees, is -1. And then finally, if theta is equal to 90 degrees, so if force vector and displacement vector are perpendicular to each other, cosine of 90 degrees is 0, so then we get work equals 0. Now, work equals 0 is not the same thing as minimum work. Maybe I should go back here and write maximum work is just F delta X. Minimum work is negative delta X. Well, 0 is 0, obviously. I'm not going to box any of these, but I just want you to think about relative orientations of those vectors, even though the result of that relative orientation is a scalar. But obviously, we still need to consider what happens with those vectors. And one other thing too, let's stick to this scenario that theta is equal to 0 degrees, right? So force and delta X are pointing in the same direction. We also can do this. Typically, we don't have to worry about situations like this where force is non-constant, but sometimes we do. Actually, before I write that, let me go back here for a sec and write a note that this is for constant F, as in constant magnitude and direction of the force. But in principle, force doesn't have to be constant. So if we have a situation where the force and displacement vector are aligned, but force is not constant, so we have force as a function of displacement or force as a function of position, we can graph it and then calculate area under the curve. And this area under the curve is what's going to give us work. Now, as soon as I said area under the curve, you should have recognized that we did mention basically identical statement just a little while ago, except in that statement, we weren't graphing force with respect to position, right? We were graphing force with respect to time. So this was force as a function of time, right? And then, yeah, we still basically had the same kind of basic representation. We said that we could find area under the curve, and that area gave us impulse. So impulse and work are not the same thing by any means, right? So different units, different calculation, different idea, and so on and so forth. But they are similar in one respect. And that is that if you have an external force acting on an object, this external force can vary either over distance or over position, over time, whatever. But in any case, that external force can alter the system. So in the case of force being applied over distance, that change to the system is work, right? That's what we are going to refer to as change in energy. But in the case of force acting over time or changing over time, that change to the system is change in momentum. So that's how those two ideas are similar. The fact that a force exerted on a system actually changes or can change the state of the system. And speaking of changes of state of the system, continuing our discussion about work and energy. So when we say work is the change in energy, exactly what kind of energy are we referring to? So let's write that down too. So types of energy. Okay, so in this class we're only going to cover a few types of energy, but there are actually quite a few out there, and I bet some of these you've heard of before. Okay, so right now we're still on mechanics, so we're talking about mechanical energy. And mechanical energy can be either kinetic or potential. There are different kinds of kinetic energy, different kinds of potential energy. We'll get to that in just a minute. But overall, if we're talking about mechanical systems, the mechanical systems possess or exhibit mechanical energies. Okay? I'm sure you've heard the term thermal energy. Okay? So that has to do with temperature. That's going to be the topic of our next discussion. You also may have heard the term chemical energy or bond energy, or maybe even something like molecular energy. So that's all kind of studied a little bit more in chemistry, but it doesn't mean that we can't mention them here. And you guys already know about these, at least something, right? There is also atomic energy. Maybe some of you know about nuclear energy. Maybe some of you know about solar energy, or radiation, or radiative energy, or light energy. So those terms are not identical, but they're used in very similar means, very similar statements. So I might as well just group them together. There is also electric energy, magnetic energy. So we'll talk about those in the next course. Okay. There is also electronic energy. So that's not the same thing as electric. So electronic energy has to do with electrons. So maybe I should even combine that sort of with atomic energy, even though those are not the same terms, but kind of falls under the same category. Okay. Some of you may bring up wind energy, so that kind of falls under the mechanical energy category, and so on. So I'm just going to put ... So energy is something that everybody kind of has a feel for in everyday speech and everyday usage, right? We use energy all the time. We use electric energy, as in circuits, daily. We talk about chemical energy or nuclear energy or solar energy as a source of powering different devices, right? So we talk about all of those terms all the time. We just never really define what energy is in everyday speech. Okay? So, like I said, in this class right now, we're going to concentrate on kinetic energy and potential energy. And then we'll briefly mention thermal energy too. And then we'll continue with thermal energy into our next unit of thermodynamics. So let's throw in some definitions. We'll start with kinetic energy. This one I've actually given you before, but now we have to really study it for what it is and know what the origin of it is and so on. So kinetic energy is energy of motion. We use capital K for kinetic energy, and it's defined as 1/2 mv squared. I'll box this. M is obviously mass. V in this case is speed. Remember our conversation about kinetic energy being a scalar, or any energy for that matter being a scalar. So we don't need to worry about direction, right? Just speed is what we care about. We definitely don't have to worry about components when calculating kinetic energy, and so on. Okay. Units, of course, units of any energy are joules. So units of kinetic energy are joules as well. So let's look at the couple of different values that kinetic energy can take. So we'll start with kinetic energy being 0. Then we also need to discuss when kinetic energy is positive and when kinetic energy is negative. So kinetic energy is 0. Let's look at the equation, 1/2 mv squared. So obviously we're dealing with mechanics now, mechanical objects, mechanical particles. So we're not going to have to worry about the situation where mass is equal to 0. Okay? Yes, there are massless particles out there, but that's definitely not something that we have to worry about when we discuss mechanical objects. Okay? So the only way to get kinetic energy equal to 0 is to have speed equal to 0. Okay? So basically, we interpret it as an object that is not moving, right? No motion. So that's easy enough. If kinetic energy is energy of motion, if there is no motion, there is no kinetic energy. Kinetic energy is positive when there is motion. So we're going to say when speed is not equal to 0, right? The object is moving. Mathematically speaking, you take any value for v. Doesn't matter if you even talk about speed or velocity there, right? You take any number, you square it, you get a positive number. And of course, mass is always positive. So as soon as the object has motion, kinetic energy is positive. Okay? So kinetic energy is never negative because you cannot have less than 0 motion. Either you have motion or you don't. And of course, mathematically, kinetic energy is never less than 0 because, well, we have that v squared in there in the expression. Okay? So keep that in mind. Now, I did mention that there are different kinds of kinetic energy. So typically, when you're told to calculate kinetic energy, that's the equation that you're going to go to immediately. But it's not quite complete. So a lot of times you will call this, you will hear this being referred to as translational kinetic energy. And you might even see the subscript for translation. Okay, so translation means linear motion. Right, so we know that velocity, we use v for linear motion, and so on. So translational kinetic energy is energy of linear motion. Now, of course, we also talked about rotational motion, right? And we talked about how laws of physics are the same, regardless of whether an object is moving linearly or rotationally. And we also know how to, quote-unquote, derive rotational motion equations by making appropriate substitutions. So what if I did the same thing here? I'm going to define rotational kinetic energy. Sometimes people even call it rotational energy. I'm going to do that by literally making all the same substitutions as we did before. So instead of mass, I'm going to use quote-unquote rotational mass, as in moment of inertia, and instead of velocity or speed, I'm going to use rotational velocity or rotational speed. Okay, so let me write that. This is rotational speed. So again, no need for direction or components or whatever, right? We know the units of that. We know how to measure it, how to calculate it, and so on. Units of rotational kinetic energy are joules, just like any other energy. Now, we did talk about situations where linear motion and rotational motion might be combined. Remember that really horrible picture that I drew of a baseball bat? Right, the baseball bat that's being thrown, and then it rotates as it moves through the air, right? So in something like that, if an object exhibits both types of motions, we may also talk about total kinetic energy, which is going to be a combination of translational and rotational kinetic energy. Now, I'm not going to box that because it's not really an equation. This is just us really saying that kinetic energy is energy of motion. So if we have different kinds of motion, we have to address them. That's all there is to it. The next kind of energy that we need to discuss is called potential energy. So when people say that energy is the ability of an object to do work, usually they are actually referring to potential energy. Okay, so if you want to make yourself a quick note here that this is what we mean when we say ability to do work, this would be a good place to do that. I'm not going to write it down, but you can. Okay, what I am going to write down is potential energy is energy of location or position. And there are a couple of different kinds. So we're going to discuss gravitational potential energy. Okay, so first let me write it like this. We use capital U to denote potential energy, although depending on what sources you look at, you might also see it written as PE or even P sometimes. So gravitational potential energy, U with a little subscript g, is mgh, or you might also see it written as mgy. We use these equations completely interchangeably. I actually prefer this one here, mgy, only because h kind of represents height. Well, not kind of, but it does. But I think it makes things a little bit more confusing if we think in terms of height as opposed to vertical position. And here is why. So when we talk about vertical position, we already know that's going to be along the y-axis. And we know that vertical position can be positive, negative, or zero, right? But height, some people have a hard time thinking of negative height or even zero height. So that's why I think writing it in terms of vertical position is just a better choice. But I will leave it up to you. I tend to use this two expressions interchangeably for problem solving. Now here is a bit of a trick here. When we say vertical position, it has to be vertical position with respect to some kind of reference point. You can't just say y equals 5 meters. You have to state where you're measuring it from. So you will hear people say something like y is equal to 5 meters above the ground, or y is equal to 2 kilometers below the surface of the earth, or something like that, right? So there has to be a reference point. So reference points are arbitrary. We define them as y equals 0, or you can also call it h equals 0, whichever. Okay, they're arbitrary, but they're used kind of based on what the situation is and what makes things simple. So for example, if I'm talking about throwing a ball up in the air, and we'll do some examples later. So if I'm talking about throwing a ball up in the air, I might want to take the ground to be my reference point, because the ball is probably not going to go below the ground or below the surface of the earth, right? If I'm talking about, I don't know, launching a spaceship to the moon, I'm probably going to take the surface of the earth to be my reference point. So it's all about convenience. And no matter what happens, whatever the problems are, you have to state what your reference point is. So even if you think back to problems when we dealt with projectile motion. Remember how we always stated, here is where y is equal to 0. And we measured the height or vertical position in relation to that 0. So it's kind of the same thing. Okay? Units are joules. Okay? And then let's also do the same thing as what we did with kinetic energy. Let's consider a couple of scenarios where gravitational potential energy is 0, where it's positive, and where it's negative. Well, we already said that gravitational potential energy has to be measured with respect to the reference point, right? So if an object is at the reference point, y is equal to 0, and then potential energy is equal to 0. So this is at reference point, right? So we say y is equal to 0. If an object is above the reference point, y is going to be positive, and therefore gravitational potential energy is going to be positive. Remember, I have to remind you really quickly that g, the acceleration due to gravity, so that's a positive number, right? On Earth, 9.8 meters per second squared, right? This is at the surface of the Earth. Okay. And then finally, this time UG can be negative when the object is below the reference point. So vertical position is negative. Now, the fact that gravitational potential energy can be negative does not make it a vector. It literally is all about how you measure things in relation to a reference point. So literally, where the object is in comparison to the reference point. That's all there is to it. It doesn't make this quantity a vector. It's still going to be a scalar. There is another expression for gravitational potential energy. So if you remember talking about gravitational forces, so we talked about two expressions for gravitational force, or force of gravity, right? We had local force of gravity, mg, and we had universal force of gravity, g, big G, m1, m2 over r squared. Remember that one? So it's same kind of deal here. I can also have u with a subscript capital G, negative big G, m1, m2 over r. Okay, so I'm going to box this. So notice there is a minus sign in the front. That's important. And there is also r as opposed to r squared in the denominator. So for universal gravitational force, we had r squared. For gravitational potential energy, we have just r. If I graph this, it's going to look like this. Okay. So very similar to the graph for universal gravitational force, right? Not quite the same shape, but very similar. And a couple of interesting points here, especially this one. I should probably even denote this in red. So this says that as r approaches infinity, gravitational potential energy goes to 0. So gravitational potential energy can be used in place of gravitational force in terms of describing different systems, right? In terms of describing interactions between objects. Since we're not plugging in any zero values into this equation, we're basically just saying that UG is negative unless it's approaching 0 for a really large value of r. Okay? So these are the two different gravitational potential energies. Mostly we're going to use this one, the MGY. We are only going to use the one for universal law when we have two different masses separated by a distance r. So basically just when we talk about things like planets and stars. But for the most part, we study things here on Earth, right, when we deal with mechanics. And so that equation at the very top, that's the one that we're typically going to be using. There is one more kind of potential energy that I need to tell you about. So this is called elastic or spring potential energy. Remember we talked about springs? So I'll remind you, you can have a horizontal spring or you can have a vertical spring. Typically it's a mass spring system, but that's fine. We already discussed that, right? So we can define this mass. We can define spring constant. Spring constant is little k. Don't confuse it with big K for kinetic energy. Okay. So you can write it as US. Sometimes you will see it written as U with subscript EL for elastic. I typically write US. Elastic potential energy is 1/2 kx squared. Box this. Units are joules, of course. Okay. Now remember what this x is. X is displacement from equilibrium. So I can define my equilibrium here at x equals 0. I can define my equilibrium here at x equals 0. By the way, for vertical springs, if you want to use y instead and write it as 1/2 ky squared, you can. It's not going to make things any better or any worse. It's just basically the same thing. Okay, so however you want to express that. And we can do the same thing as before. We can analyze what happens with this value. So we can write the list of situations where spring potential energy is 0, where it's positive, and where it's negative. Okay. So since spring potential energy depends on displacement, that means that US is going to be 0 when x is equal to 0. So no displacement, the object is at equilibrium. Okay. US is going to be greater than 0 when the object is not at equilibrium. Notice that the pattern is actually very similar to the pattern with kinetic energy. So either this object, this mass spring system, either it's going to have potential energy or it's not going to have potential energy, right? So K is a positive constant, and then mathematically speaking, X is squared. So you're not going to get a negative value out of this. Conceptually speaking, you can say either the spring is at equilibrium or it's not. So there is no third choice there. Okay. So that's spring potential energy. Let me also briefly mention thermal energy. So we'll talk more about thermal energy when we discuss thermodynamics, but I'm just going to define this briefly. So thermal energy is basically the total of individual kinetic energies of all the particles. So if we're talking about a system of particles or even an object made out of individual particles, all of those individual particles can be moving. And as they're moving, they obviously each individual particle has kinetic energy. So if we add all of the individual kinetic energies of all of the individual little particles, we'll get thermal energy. In everyday language, people would loosely say that thermal energy is the same as heat. Okay, so in physics, that's not the case. But again, that just kind of to give you an idea where we're going with the next unit when we get to thermodynamics. So for the time being, you can say heat is equal to change in thermal energy. Okay, so for now, I'll box it, but this is actually not, strictly speaking, a correct equation, or rather, it's correct, but it doesn't apply to everything. Again, something that we'll discuss later. Okay, so capital Q represents heat. So thermal energy and heat are not exactly the same, but change in thermal energy can be, in certain cases, thought of as heat. Okay, we'll come back to that. Okay, so the last thing that we need to mention in this set of lecture notes is power. Okay, so power is denoted by capital P, although I don't ever write it like this for power. I write it either like this, or I even write curly P, cursive P. And the reason is that regular P is also used for pressure, and there are situations where those two quantities have to be combined into this single equation. So obviously we don't want the same variable representing different things in the same equation. So I use one of these notations to, distinguish power from pressure from regular P. And we'll talk about pressure later. So definition of power is literally change in energy over time. Okay, so most commonly you will see power written as delta E over delta T. Okay, and I suppose I should box this. But remember that delta E is also work. So we can also define power as rate of doing work. Of course, the word rate represents the fact that it's done over time, right? So we know that. Okay, so it's either change in energy over time. We can say also transfer of energy over time. We can say rate of doing work. Okay, we can say rate of transfer of energy, and so on. So there's different combinations of those words that you can use to describe power. When I write this equation, I actually typically write out the word work as opposed to just using W. And the reason for that is because the unit of power is also denoted by capital W. And capital W in this case stands for watt. Okay, so unit of power is watt. So if you look at any electronic device in your home, doesn't matter what it is, microwave, light bulb, whatever, you will see a rating on that device that says something or other, kilowatts. Okay, so or even watts. So that's the power rating of that device. So watt is defined as joule per second because, well, it's joule for work or change in energy. Second is a unit of time. Okay, so this is the unit of watt describes the rate of energy transfer. So this is why I don't usually write it as W over delta T. I usually just write out the word work, or I use delta E, because I don't want to use W twice in the same equation to denote different things. And it is capital W. Okay. Now here is a word of caution. Notice that I wrote delta E over delta T. I would never write delta W over delta T. This is bad. So remember, definition of work is already change in energy, right? Or we can also talk about transfer of energy. So if you write delta W, that means change in transfer of energy or change of change. That kind of makes no sense. It's kind of useless. So don't ever write delta W. You can only write either W over delta T or delta E over delta T. Okay? Now, because we define work also as force times displacement times cosine theta, there is one more way of writing power. So think about taking both of these quantities and dividing them by delta T. What's this here? What's delta X over delta T? Yeah, that's velocity. So we can also write this expression for power as FV cosine theta. So this is only, both of these equations are only good for constant force. Okay? And most of the time, you're not even going to see that. Most of the time, you will see this equation written as FV. So like, for example, if there is a force that makes an object move, and the movement is velocity v, is expressed by velocity v, then we say that power is Fv. Yeah, it does imply that F has to be in the same direction as V, just the way that I drew it. But that's the most common way of writing that equation. So this one on top here, that's the definition. This is what you will see most often. But in terms of mechanical systems, where constant force is acting and the speed is constant too, that's when you'll see this other expression. This is only good for mechanics. But the expression, the definition of power being rate of energy transfer, that's good for anything. And you'll also see that equation in magnetism, in nuclear physics, and so on and so forth. So there is all kinds of application of that top equation. Okay, so this should be everything that we need to know about work and energy, except the biggest idea that has to do with energy, and that's conservation of energy. So we'll make that a separate topic just because it's so important and it's such a big idea. So we'll have the next set of lecture notes is going to be on conservation of energy.